Thank you very much for coming today. We have a lovely guest, Scott from SMA. So Scott graduated here from with the first class in 2003. So it's always great to have alumni here, especially from the first class, from the special one. After that, he worked in CSG Solar here and in Germany, and joined after that to Suntech R&D. And then I had the pleasure to have a bit of collaboration with him. And from 2014, he's with SMA. And if you remember a few weeks ago, Jono spoke about problems with system, and we highlight the fact that in inverters is one of the main problems. So we thought, let's bring SMA to explain how you need to do good inverters. So please welcome Scott, that came a bit sick, so be patient with him.
Sure. All right. Thank you. Yeah, I'm halfway through a bout of glandular fever, so if I need to sit down, don't be alarmed. Thank you for the opportunity, Ziv, to come and talk today. So I've been invited to give two talks. The talk today, I'm planning to just give you an overview of inverter technology, where it started, how it's looked at, how it's changed over the past 25 years from an SMA perspective, and then also how inverters are used to help realise the smart grid, which is something that a lot of people keep talking about today. And then a follow-up talk, I think it's next month, is going to discuss all those issues of, reliability and failure mechanisms, and which inverter technology might be the most appropriate for certain systems. So if you have any questions, feel free to just throw them out, or you can hang on to them until the end. Standard legal disclaimer, all care given, none taken. So before I started talking about inverters, obviously Ziv mentioned I'm a PV alumni, and you might have seen the ads recently about a little lump of coal and what an amazing thing it is. Well, that's a little lump of silicon, and I think it's a much more amazing thing, 2,000 times less material to generate the same electricity. So we should all feel good about what we're doing, because that's something special, I think. So who or what is SMA? SMA is an inverter manufacturer. At the moment, we're the largest inverter manufacturer in the world. Started in 1981, same year I was born, and it has over 36 gigawatts of inverter products sold throughout the world, mixture of microinverters, string inverters, and central inverters. And to get an idea of our scale and our presence in the market, 1 in 3 inverters on the planet is an SMA product, and at the moment, 1 in 4 inverters in our country is an SMA product. So hopefully my perspective about inverters is valid given the company's experience. Systemesanlagentechnik. Apologies for the poor pronunciation, but essentially that's SMA, and the company started in 1981, was built around these ideas of computer control, measuring, and plant systems and plant technology. So that's what SMA tries to achieve through the delivery of inverters. So a lot of us who have come from PV engineering have a really good appreciation of photovoltaics and PV modules and how they're made, how to make them well, what not to do. But I know that during my time here, I never really got much of an appreciation of the inverter. And the inverter is a really important thing for solar, because without it, the large-scale uptake that we've seen across the world over the past decades probably wouldn't have been able to be realised. So what's an inverter? What's critical for it, and how does it work? I suppose there's 2 really important things for an inverter, 2 really important functions that it has to do. The first thing is, obviously, on the left here, you can see we've all seen these IV curves, maximum power points. One of the main functions of an inverter is to track that maximum power point and try and find within, whether it's at a micro level, a string, or a central inverter level, try and find that maximum power point to ensure that the greatest amount of energy is being realised from a PV plant. And that's obviously part of that computer control and measuring technology that's part of what SMA try to do with their products. The other important bit is, while DC is good, our whole electricity network is built around AC. And so the other main function of an inverter is to take our PV DC electricity and turn it into AC, and whether that's in an off-grid situation where the PV inverter has to actually form the AC sine wave and be the grid, so to speak, or whether it's in a grid-connected system, which is what 1.4 million PV systems in Australia are, and it's looking at the grid, measuring it, and then copying the AC sine wave to ensure that that PV inverter is able to sync to the grid and its electricity be used. So it sounds pretty simple. That's really what we're talking about with an inverter. So we've got our maximum power point tracker. We've got things where we have to look at the voltage from the PV modules, measure those, play around with it, push it up, push it down to try and find that maximum power point, have feedback loops. We obviously need to take that DC and pass it through a circuit and convert it to AC. And then we need to, obviously, that AC output needs to mimic. I won't spend too much time on this, but that's just to give you a general sort of block diagram idea of what an inverter is and how it works. So the way that a maximum power point tracker within an inverter will work, and apologies for the type font, it will initially let the PV array do whatever it wants to do, and it will take that as a first reference point. And then within the inverter, it will bias the PV to play around and try and find where the maximum power point is. And this illustration here is meant to show what happens within an inverter very, very quickly. So here I'm stepping through very, very slowly. This happens within the inverter in sort of millisecond to second time frames, where the inverter will continually push the voltage of the array around, try and identify this maximum power point curve and work out where that maximum power point is, and then try and hold it steady. And obviously, with the PV system, if it's sitting statically under a perfect light source, that's a really easy job. But that's not what happens in real life, and the sun varies constantly. If you've ever been out on the roof with an insolation measurement device, you'll notice that your watts per metre squared goes up and down all the time, and how that impacts each individual PV module is different, and then how that affects a PV string is different. And so this process is happening continually. Clouds pass, and so we might slide all the way down the curve, and we need to make sure that the inverter needs to make sure that it's able to recognise events like that and respond to them, and then always make sure that it brings the output of that PV array back to its maximum. So it's always happening. It's a process that happens constantly within the inverter, and it happens, as I said, on the millisecond time scale, and it's why it's one of the most important functions within an inverter. So the other part of an inverter is obviously converting the DC into AC. So what I've got here is a very simplified circuit diagram of a single phase transformerless inverter with a H5 bridge. So each of these switches here is an IGBT, an insulated gate bipolar transistor, so it's just a switch essentially. And so I've got them represented here as switches to show you how we're able to take a DC that might be at, say, 500 volts plus, and turn it into our 240 volts or 230 volts RMS AC output wave. And so you can see here we've got our PV connected, and then in the first part of the process converting DC to AC, you have some of the switches close that allows current paths to flow through out to the AC side. And you can see here what I've got on the right hand side is showing what the DC voltage is doing through, or what the DC is doing through each of those switches as it makes its way through to the AC side. So in the first step, we've got positive DC voltage. Our next step, we start making our 0 point. So 0 DC voltage. You can see switch 5 opens, switch 1 remains closed, switch 3 closes, and so we're starting to generate a very ugly sine wave. Yeah, it's very stepped. And go on to a third step where we start to then generate the negative part of our AC sine wave and complete that to a minimum. Now, what you can see here in the bottom right hand side is what potential is seen through each of those switches during the process. And these switches will be operating at high kilohertz frequencies, and so the switching is happening constantly to chop up and change our DC voltage into the AC sine wave that you would have seen on oscilloscopes in labs, hopefully. I can't remember if I did it when I was a student. But it ends up looking pretty ugly. It ends up still looking a little bit ugly, and so then that signal which is coming out is passed through filtering, AC filtering, and that's where we end up with our nice, smooth, this dark blue line AC output. The other thing to note is that with a transformerless inverter, there's two types of inverters, and I'll talk about this a little bit later, but a transformerless inverter means that there is no electrical separation between the DC and the AC. So the DC voltage is tied to the AC, and so as the AC voltage rises and falls, the DC voltage also is forced to rise and fall. Now, that doesn't mean that the DC goes down to 0 volts and no power. All it means is that its reference to Earth changes all the time. So there might be a 500 volt DC string. The 500 volts will always remain, but it may be that at one point in the cycle, that maximum voltage has 500 volts down to Earth, whereas at another point in the cycle, the maximum may be, say, 250 volts to Earth, and the maximum negative could be negative 240 volts with reference to Earth. And for those of you that have a good appreciation of PV and some of the reliability issues that can arise, you'll automatically see that that gives rise to conditions that can cause PID, potential induced degradation. So, and that's something I'll cover a little bit more in the talk next month, or I can answer questions about it later. So, the other important thing that a PV inverter needs to do is it needs to do all of this maximum power point tracking and conversion from DC to AC. It needs to do it efficiently. It's no good having an inverter that's cheap, robust, and able to convert DC to AC, but it's only 20% efficient. There's a lot of time, money, and effort that goes into that solar panel, and as a result, there's been a strong focus over the development of inverters to maximise the output of that PV. Now, obviously, that stems from the fact that PV, before all of us started studying was, $10 a watt and above. Now, obviously, with the price of solar going lower, the efficiency of the inverter is not as important. It doesn't need to be, as close as it can to 100, but it's still very important to be quite high, because with PV, we're talking about a means for people to reduce their costs from grid electricity or reduce their costs from running a diesel generator. And so this investment that they might make in PV needs to be maximised, and that's why the efficiency is important. And there's a couple of ways that efficiency is looked at. As with most things in life, most of the world looks at efficiency one way, and Americans come up with their own method to define efficiency. So I guess there's 2 points to look at. You can see here I've got two curves of two efficiency curves of inverters, and you've got inverter A and inverter B. Now, if you're only looking at a single number and you said, what's the maximum efficiency of that inverter? You'd say, inverter B, that's the one for me, 100%, that's perfect. But obviously, I pointed out that, and we all know, our PV is never operating at a single point, it's always changing. And so what's actually more important is how an inverter's efficiency looks throughout an entire spectrum of power output or voltage inputs. And that's where some of these European weighted efficiencies, or the CEC efficiency, which is not the Clean Energy Council, it's the California Energy Commission. That's where these look to measure and benchmark inverters so that within industry, system developers can make the best decisions for their individual plant. So the way the European efficiency works is that it knows that a PV inverter never operates at 100% power for 100% of the year. If you looked at the output power of an inverter as it relates to the PV, this is approximately the distribution that you would get. About 50% of the time it's operating above 50% power, and then the rest of the time it's below 50% power. And so with the CEC, with the European efficiency, they try to weight each of those according to this table here to come out with a lumped efficiency number for the benefit of the system developer. And there's lots of things that you can do within the design of a PV inverter to change how that curve looks, or to see where it peaks, or to see how flat the curve might be. It can come down to the selection of the IGBTs, how complex the circuit is, what frequency those IGBTs are switching at, whether it's a transformer-based or transformerless inverter. And so the Americans are kind of the same but different. They ditch one point and pick up another one. It's reasonably close. It's a lot closer than it is between the metric system and the imperial system, which is nice. So, okay, mass production of PV inverters. So one of the reasons that photovoltaics was able to get so cheap over the last 20 years is because it went from being something that was produced in small volumes to something which is mass produced, full scale, 24 hours a day, 7 days a week, 365 a year. Same with inverters. It's come a long way in the last 20 years. As you can see there on the left, that's a picture of the first mass-produced inverters from SMA. It looks very much like the old electrical engineering building laboratories, I think, where they were making less than 1,000 pieces a year. It was a little workshop, and every single inverter was made by hand, compared to today, where the manufacturing is all inline, automated. It has various quality control, automated quality control, and you can see here, obviously within SMA and within most inverter manufacturers now, they'll produce volumes in excess of, or they'll have the capability to produce volumes in excess of 1 million units per year, which has been one of the main drivers to bring the cost of inverters down as well. So what I'd like to do is just take you through the basic manufacturing process for an inverter. Some of the steps along the way, some of the quality control processes, testing, and then what happens before an inverter goes out the door and before it goes to, you know, an installer or a system developer or whomever. And most of the process in building an inverter is around circuit boards. So if you opened up an inverter, you would see anywhere between 1 and 4 circuit boards, and you would see, you know, hundreds of individual components which are all automatically placed, automatically soldered. Throughout the process, there's automatic inspection to check that the right component has been placed in the right place, that it hasn't been placed upside down, that it isn't missing. That throughout that process, certain parts of a circuit board will be tested to ensure that they're functioning correctly, and that all of that data, as within any quality management system, goes back and is reported and stored so that if field failures happen later, the data can be cross-referenced to try and find out, was there an issue in production? And then boards are coated, protected, so electrically insulated, and then finally completed where they go to testing. Now, Zib, I don't know if this presentation is being made available to people, but you can actually go and have a look. There's a YouTube clip that SMA made that shows the production process step by step. It runs for about 10 minutes, so I didn't want to play it here, but coming from a non-inverter background before I joined SMA, I actually found it quite instructive and interesting to know how they're made. It reminded me a lot of the old virtual production line subject that we used to do. So once all of the circuit boards are through the production line and manufactured, they're put together in a unit. Now, some of that can be, depending on which inverter it is, some of that will be a manual process. So with the larger central inverters, the process to build the inverter can sometimes be as long as 8 weeks, whereas a smaller string inverter or a microinverter is produced in less than a day. Now, with those smaller units, boards are automatically tested, automatically installed into the inverter. And then once they've been assembled, they go through for testing and burn-in to reduce infant failures. So, and then you can see here on the right, I don't know if anyone's ever done PV module testing, humidity freeze or something like that, but it's a very similar process that inverters will go through for environmental testing to make sure that they're fit to go out into the field. Because just the same as the PV modules that are connected to them, they're exposed to the elements and they need to ensure that they last hopefully as long as the PV modules that are connected to them. And then depending where it's going around the world, it might get, you know, an instruction manual in Thai or an instruction manual in Swahili or Australian, different sticker, packed up and goes out the door. Now, inverters have changed quite a lot over the past 25 years. You would say they've probably changed a lot more than PV modules have changed over the last 25 years. And given that SMA was the first manufacturer of photovoltaic string inverters, SMA has seen quite an immense change between what their first products look like and how they perform those critical functions of maximum power point tracking and conversion from DC to AC to what is realised now. So I'll split it up, single phase and 3-phase technologies. So that is the first mass-produced PV inverter anywhere in the world. So it had maximum power output of, I've forgotten, I think it's about 700 watts. It was a transformer-based inverter, a high-frequency switching transformer, and you've got a picture of the circuit diagram there. But, you know, one of those points that's really important for an inverter, back then, 90% efficiency. So obviously a long way off the ideal 100%. So that was back in 1991. And it was inverters reasonably similar to this, about that. That's an inverter that I think has a bit of relevance for us here in Australia. So this was the next evolution, which moved to a 50 hertz transformer-based inverter. So, and when I say transformer-based, I mean physical separation between the DC and AC. So there was an isolation transformer that was part of that DC to AC conversion. So it was a 50 hertz transformer. Production processes improved, they reduced the number of parts, and so you can see here, that's also a 700 watt inverter, and it went from being something like this to being something like this. And the reason that those inverters are of interest to us here in Australia, anyone ever been out to Olympic Park? You've seen the big towers with all the solar panels? Inverters very similar to that from SMA is what's connected to those solar panels there. So that was, I guess, approaching 20 years ago, and that's one of the advantages of transformer-based inverters is that they're very robust, about as robust as a boat anchor. You almost can't kill them. So 93.5%. So you can see that the efficiency is slowly improving. The major efficiency gain, though, for inverters came when they moved from being transformer-based to transformerless inverters. So part of the reason that move came is because a transformer is inherently inefficient. There's quite a lot of heat loss. There's quite a lot of material in there. So again, we're looking at an inverter here that was slightly higher power, so about a kilowatt compared to the previous inverter, which was 700 watts. But whereas here we've got something that weighed about 25 kilos, here we've got something that weighs about 16 kilos. And so you can see here that part of the improvement in the technology over time is not just the efficiency improvements in going from transformer-based to transformerless, but also a reduction in component numbers. And anyone that's done microelectronics or circuits will know that the reliability of any circuit is dependent upon a number of things, but one of those things is the sorts of components that are in that circuit and the quantity of components that are in that circuit. So by reducing the number of components in the circuit for a PV inverter, it was able to deliver quite a substantial improvement in reliability, which is a really important thing for solar if it's going to continue to be a major source of electricity supply around the world. Slight iteration, slightly different transformerless inverter, a little bit better, new improved, the AC filtering was getting better and better, so whereas sine waves back in 1991 might have looked rather jagged and ugly, they're starting to get towards a very smooth, pure AC sine wave by this point. One of the problems until that point with a PV inverter was that the DC window with which it was able to operate, with which its maximum power point track was actually able to work, was quite narrow. And that meant that with the design of a PV system, it could be somewhat restrictive in what sort of PV modules you could use, or how long the strings could be, but also there was also a floor that meant they had to be at least a certain number, and that window between the minimum number and the maximum number was quite small. One of the developments that happened in the early 2000s was the changing of that DC input to have a step-up converter. So it meant that the DC input window was able to be essentially doubled, which gave a lot more flexibility in the way that photovoltaics was used. It gave a lot more flexibility because obviously around this time PV was changing, the forms of modules were changing, the voltages of them, the currents, and that's an important thing that an inverter needs to always remember, is that it has to somewhat conform to the PV modules. PV modules now also have to somewhat conform to the inverter, but at this point in time, it was very much the inverter had to meet the requirements of the PV module. So the additional circuitry there was able to increase that DC window. The improvement to that circuit was what SMA then came up with, which is the H5 bridge, which is the 5 IGBTs that you can see there, and that's the illustration that I showed earlier, which saw efficiencies peaking towards over 98%, weighted efficiencies up to 90, again almost up to 98%. But again, that progression is always seeing a reduction in components, a reduction in complexity, which is always leading to an increase in the reliability of the inverter. So, and that's about where single phase inverter technology stands today. Even though this was, back 2005, it hasn't changed too much. The circuits have been able to be more compact, the selection of components has been able to be refined, the individual components are more efficient now, but essentially this is still what, if you open up an SMA inverter or even some other competitor inverters, you would see a circuit very similar to this. And then everyone decided to go back to the future, and they didn't want transformerless inverters anymore, they wanted transformer-based inverters. So then SMA went to the effort of trying to come up with a transformer-based inverter, which was, able to achieve reasonable efficiencies, reasonable DC voltage windows, wasn't too heavy and didn't have too many components. And a lot of this push came because of thin film modules which required grounding, but also some PV module manufacturers requesting that their products be installed with the negative pole grounded, which if you have a transformerless inverter is not possible, because in that case you would have a direct short from the AC side to ground. Hence this inverter, which is no longer manufactured, and no one wants this sort of thing. So, and then the other technology is three-phase technology. So, most businesses will operate on three-phase power. A lot of homes will operate on single-phase power, so all of those previous class of inverters are suitable for them. But when you move into, say, a commercial system, so there's a large PV system on the roof of this building, that's a three-phase connected system. It needs to rely on a different technology to the single phase, or you need to duplicate 3 inverters, one for each phase, which less reliability, more components, more cost. So this was the circuit design for the first central inverter that SMA produced, so a central inverter for a large utility scale plant. It was, from memory, about 125 kilowatts, so at the time, huge. The little red ones, or the little blue ones, we were talking about 700 watts. Here we're talking about orders of magnitude greater. However, this is a transformer-based inverter, 50 hertz. And pardon me, the problem with that circuit topology is that it's not suitable for simply using as in a transformerless arrangement. And the reason is that it comes down to that component I talked about before, the IGBT, the insulated gate bipolar transistor. They have different voltage ratings, and depending on what your application is, you might need to use one which is, say, 600 volts rated, or 1200 or 1700 volts rated. Now, to get an adequate DC input window for the PV which is being connected to the inverter, if you were to use this topology for in a transformerless arrangement, you'd need to use IGBTs that are, up to 1700 volts. And the problem with that, it actually becomes way too complex, and it's far too inefficient for the end device to actually use that. So the circuit design had to change to this. And so they had to, as with the advent of the H5 bridge, which was able to increase the DC input window. A similar concept was then applied to the three-phase circuits that then allowed three-phase inverters like this, and I'm pretty sure these inverters might be on the roof of this building as well. Allowed inverters like this to be mass-produced, and you can see there were certain forms of this product that were manufactured that had peak efficiencies over 99%, and that's where the technology today is trending towards, across all manufacturers, always pushing towards greater than 99% efficiency. So, how have inverters improved? So you would have seen, well, maybe some of you might have seen a similar curve for PV modules over the past 20 or 30 years, that as learning with manufacturing and as volumes increase, the price is always coming down. And so you can see here two different curves, and this is, while this is SMA, this is broadly true of the entire industry, is that there's been a learning curve of about 20% and for string inverters for the smaller ones, and a learning curve of about 10% reduction in price per annum for larger central inverters. So, and as the market for PV continues to grow, these prices are going to come down further and further, which is only good for all of us, really. So, yeah, and that's just a look at what the efficiency has done throughout that development. So you can see originally starting at just above 90% to now, so that inverter there, which is a 20 kilowatt inverter from SMA, still holds an efficiency record of a touch over 99%. But the components to make it a little bit expensive, and so in the end it's not something that anyone really uses now, especially because PV panels have got so cheap. The efficiency of the inverter is not so important anymore. This is a slide that one of my colleagues in Castle sent me. So he works part-time for SMA and part-time as a professor at the University of Castle. But he's just showing here how each of the different technologies has come down, has improved their efficiency. So with the first sort of technology, it was taking it took 15 years to cut the efficiency loss in half. For HF inverters, so high frequency transformer-based inverters, they were produced at higher volumes, and that efficiency loss was cut in half within 12 years. Transformerless inverters have seen the same cut in the efficiency loss in 4 years. So the same as with PV, as the volumes have got larger and larger, the prices come down a lot faster. The efficiency of inverters is improving at a faster rate with the uptake. PV inverters, so they've got a lot more reliable, a lot more efficient, and a lot greater. They've integrated a lot more functionality. So, and it's that functionality that is probably really important now, because as solar becomes ever more prevalent in the grid, the ability of our electric power grid to cope with that solar is being tested. We have electric power grids around the world that were designed pretty much 50 years ago. They had a design principle of centralised generation, high voltage transmission, some medium voltage consumption, but medium voltage transmission, and then consumption at the low voltage grid, which is what these lights are all plugged into. So they were never designed to have energy generation at the other end, pushing it all the way back up that flow. So, and that's really one of the challenges for solar and also for inverters into the future, is to allow the grid to be smarter, to allow there to be a greater match between generation and load consumption, so that energy is able to be delivered at the most efficient price. So, you know, this is what the homes are starting to look like now. They're starting to not only have solar in there, they're starting to look at things like automatically controlling loads to switch them on and off depending on whether there's spare solar. Everyone talks about batteries. Batteries are going to be integrated in. There's a picture here over on the left-hand side. You're looking at a car. Everyone's also talking about electric vehicles. All of these things are functions which the PV inverter is starting to integrate and control. And the other part of it is the grid support function. So I mentioned that our grid was never designed for solar to be installed at the end and pushing power back up. And that creates a lot of problems for the grid operators. But there's lots of things that PV inverters are able to do in the way that they convert DC to AC to make that a lot better for the grid and to allow, therefore, you know, increased penetrations of, you know, towards 60 and 80% into the low voltage grid. And some of these graphs are just showing what, you know, there's an Australian standard which defines how inverters are supposed to operate when they're connected to the grid. And there's been people at UNSW who have had a lot of input into the development of those standards over the years. And these are just some of the functions that inverters are now able to do, such as, you know, depending on what the line voltage might be doing in the grid, they might change their active power and their reactive power components. They might change their AC output power depending on frequency or depending on line voltage. They will increasingly be able to communicate directly with the utility at the low voltage grid level. This is something that's already possible at, you know, larger commercial installations or utility scale installations, but at the low voltage grid level, they'll be able to respond to a utility directive to maybe decrease their output, increase their output, change the way that their output is. And, you know, functions like this, actually giving people who are purchasing PV systems and using them, giving them information to help them make the most efficient use of their solar. They've made an investment, and it's very important for that investment to be worthwhile for them and to give them a good payback. And as with anything in life, information is key to making the most of whatever it is you've got. So, I'll finish there. I guess this picture is probably less, well, since we've had a change of Prime Minister, there's less people looking down, there's more people looking up, so I guess that's nice. But that's what I have today, and thank you. So I don't know if anyone had any questions or they wanted to ask anything about an inverter or PV or, yeah.
Can you add a few words about microinverters?
Yeah, so there were a couple of topics that Ziv sent to me that he said it'd be really good if you talk about that. The differences between micros, strings and central inverters, reliability of those, typical failure mechanisms in inverters and how that corresponds to yield losses within a PV plant. That's all subject for a follow-up talk. So I have lots of information. I actually wrote a blog post on it, published it about 2 weeks ago on our SMA blog that talks about the differences between microinverters and string inverters. So,
has anybody who doesn't have a vested interest written about it?
I would say I don't have a vested interest in it, and I've written about it. So SMA is probably unique within the industry. It makes microinverters, it makes string inverters, it makes central inverters, and really from SMA's point of view, they don't care which inverter you use, just that you have one which is highest quality, highest reliability, and best efficiency, but most importantly is the most appropriate technology for the individual application. So in terms of no vested interest, I would say, yeah, I don't have a vested interest, so have a read of it.
And we will have another talk, like we said, in 4 weeks from now, so end of November.
Yeah.
That will be the part 2 of this one.
Part 2. That's where you can start throwing rocks if you like. What? Rob, you had your hand up first. You beat Martin.
Something that you showed was that central inverters have always been, seemingly from your graphics, that they've always been cheaper per watt than smaller inverters.
Yeah.
So
Why?
Why is that from your perspective?
If you looked at a central inverter and you looked at a string inverter and you counted the number of components in them, even though the string inverter might be, say, we'll say 20 kilowatts, but the central inverter might be 1,000 kilowatts or a megawatt, the difference in the number of components is not that much. So we're just talking about, rather than having to, increase the number of components in line with the power output, you just need to change the ratings of the components that are used. And that's one of the main reasons is, if you buy one of something small, it costs you X, and if you buy one of something which is a lot larger, it ends up costing you less, because from a manufacturer's point of view, the amount of effort to produce that component or this component is about the same, so they have to factor that into the price of it. So that's essentially where it comes down to. And from a manufacturing point of view, while I said it can take up to 8 weeks to make a central inverter, and it is still largely put together by hand, that's 1 or 2 people putting together an inverter in 8 weeks, and they've got, maybe it's 1 megawatt or 2.5 megawatt inverter going out the door. And the amount of effort, or the time to produce the same number of string inverters and the number of components to produce the same power output would be much greater at the string inverter level. So that's broadly speaking, that's why. I mean, look at PV manufacturing. When it was a 30 megawatt plant, they had a specific cost, and they found that they could actually turn their 30 megawatt plants into 100 megawatt plants by running them all the time, so they didn't have to invest in new equipment. They just had to run it longer, and there was only an incremental cost in the price of goods sold. So does that answer? Yeah. Okay. Martin, yeah.
Yeah, PV modules are very reliable, and a lot of the costing now, probably assumes an annual degradation rate and a bit of OM&M to try and capture that in the economic analysis. Like some of the early analysis with inverters would assume you have to replace them halfway through the system life or something like that. So what's the present situation now in terms of inverter reliability and relativity to modules?
If I was outside Australia, I could probably say a 20-year lifetime on an inverter is not unreasonable when you're buying a quality one. But Australian consumer law makes it difficult to say that in Australia, so I obviously haven't said that in Australia. Some inverter suppliers, you'll need to replace it halfway through the lifetime of a PV plant. But I mean, from a central inverter point of view, so let's look at utility scale solar, which I think is about 55% of what's been deployed globally. Central inverters are designed, built and delivered to match the same lifetime as the panels which are connected to them. And yeah, they will experience some component failures throughout their life, but they're designed that those components can be switched in, switched out. There's O&M contracts that mean that all happens and that the plant keeps operating. But look, I mean, we all assume that the PV lasts for the 20 years, and if it's built properly, it does. But I know that our service line engineers get lots of calls and they say, yeah, my system's not working, your inverter's broken. And after some investigation, they say, well, actually, your PV modules, they're either dead or they've got PID or there's something wrong. And so I guess it comes down to maintenance. Nothing is maintenance free. So if properly maintained, an inverter should be able to meet the same lifetime as a PV panel. You would say about 20 years.
So would it be the same steady degradation, or they'd stay more rock solid in terms of performance?
I don't have a lot of data on that other than anecdotal conversations I've had with colleagues in Germany, but essentially there is a slight degradation in the performance of an inverter over time, but it's not the sort of, 100% down to 80% of output power that you would assume with a PV module. It stays a lot more rock solid, and it's also one of the reasons that in utility scale solar plants and large commercial installations, they'll tend to oversize PV arrays so that from day one, the voltage window, they might be sort of at the upper end of that voltage window, and over time, as the PV modules degrade, they're still within that voltage window. So the voltage window within the inverter doesn't degrade. Its AC output doesn't really degrade that much. It's still, if it's delivered as a 5 kilowatt inverter, it's still almost a 5 kilowatt inverter at the end of its life, or until some component loses its magic smoke, which doesn't happen that often.
So when you say maintenance, what sort of maintenance do you mean?
It's different with different technologies. So like for example with SMA's microinverters, there's pretty much no maintenance you can do. It's all a completely sealed unit. There's only about 150 components inside, and if you were going to do maintenance, it's going to cost you a lot more than it would to just replace the unit. So you replace the unit. With larger string inverters, there are things that you might do, like in terms of, say, clearing the cooling fins. There might be things like firmware upgrades that, obviously with an inverter, there's a lot of computer control that happens in there, and a lot of the improvements that can sometimes happen are simply just a software upgrade, and so maintenance might involve that. There might be some components like varistas which offer protection to the inverter that you might say, we'll change those out on a 5-year time scale, just to make sure that if there's a grid fault, if there's a fault on the AC grid, the inverter will still be protected and that this component hasn't failed. But essentially, most of the components within an inverter are, fail open circuit. Yeah, if they fail, the inverter stops working. So, I don't know, inverters with active cooling, you might clean out the ventilation. I know that there was, in central inverter plants, so big utility scale, they need to make sure that they go around and that all the fences to the PV plant are, up, and that no sheep can get in and decide to sit down in front of the hot airflow outlet from the inverter in winter and cause the inverter to stop. So, there's all sorts of things that you can do that you might need to do to keep that plant operating. But yeah, I can talk about that a lot more in the next talk. There's a lot of really interesting information from not SMA companies, so other companies that have been operating plants for 10 and 15 years, and they have real data out there in the public domain. So
it seems that we have class after us, so maybe keep the question either to...
I'll walk outside. You can ask me questions outside if you like.
Let's thank Scott again. Great job.
Thank you.